This video is a process capability outline and design point demonstration for the IAV systems design process. Key requirements involve both design and test of a design process and a subsequently derived electric UAV. The interlinking, emergence, and nonlinearity inherent to aircraft design creates a complex, evolving, and challenging problem for engineers, and not knowing precisely how one variable changes another within the system can lead to a descent into chaos. Complexity theory identifies a number of such challenging behaviors, and we propose to address this by using systems thinking to view the process as an adaptive system. The first step in process creation is to list and categorize the process requirements for particular tools, methods, or goals. Once the process requirements are understood and interpreted, we can then conceive the process framework. The resulting self-updating 4-point process uses information modeling as a tool to produce a navigable design process database. Processes are then executed by use of the integrated toolkit, and the resulting feedback from the design solution drives process updates to iteratively improve the design algorithms. We now explore this system in greater detail. The first step in transforming the product requirements to the final design space is the definition of inputs, design processes, and outputs, but the complex and nonlinear design problem presents a challenge as to how to define, categorize, and structure these raw elements into a systematic workflow. By using information modeling, we have created the Information Model Navigator, or IMN, a navigable design process database that structures the applicable design theory and practice into a detailed, ordered, and intuitive interface. Similarly, by integrating and optimizing the individual modular tools designed to execute specific tasks, we have created the ITK, the Integrated Toolkit, a unified, structured, and dynamically updating software solution that allows rapid UAV design through a clear and intuitive interface. Tools have been designed such that the product may be optimized for a range of customer-desired characteristics. The code shown here, for example, optimizes wing position by considering the effects of other variables. This guards against the risk of accidental sub-optimization of the product by the process user. The process is now ready to accept customer aircraft requirements to create the design solution. The IMN provides a multi-level cross-linked, ordered reference schematic of the design methodology to be used by the customer, and is composed of 3 levels. Level 1 provides an input-output summary. Level 2 shows a process summary with input-output flow and methodology breakdown, and Level 3 shows full process definition and complete methodology, and is capable of easily navigating large, multi-page charts. Interdepartmental cross-linking is fully supported with the use of input-output trace buttons. The user is then able to execute the design methodology by using the IMN in conjunction with the ITK. The intuitive and dynamically updating graphical user interface allows straightforward editing of the design inputs to rapidly calculate and provide final output parameters using both mathematical tools and component databases. The use of design tables enables the control of computer-aided design software from within the ITK to provide real-time creation and editing of parametric CAD models. The design process also has sufficient flexibility to accept user-specified decisions to produce varying configurations. For example, to produce single or twin motor configurations for varying customer requirements. The required environmental performance and geometric parameters are extracted from the ITK to create MATLAB and X-plane models for simulated flight testing. A rigorous flight test plan is implemented to ensure correct performance in a range of conditions, and simulation output reports allow potential errors or faults to be highlighted and resolved before entering manufacturing. Additionally, the simulations may be used for pilot training and familiarization. Finally, the aircraft is ready for manufacture and assembly. This is again initiated from within the IMN. And the aircraft is then verified through the institution of a comprehensive battery of static and flight tests. In conclusion, the created electric UAV design process is robust, flexible, and usable, and a philosophy of systems thinking has underpinned the process design framework. Finally, the process has been partially verified by being used to design a UAV to meet the specified customer needs.